Consider an image encoded in a wide gamut color space, such as ProPhoto. When we convert this image to a small gamut color space, like sRGB, color values are clipped to fit the smaller gamut. If we convert back to the wide gamut color space, the clipped colors cannot be recovered. This results in noticeable color loss. We propose a solution to this problem. During the initial color space conversion, a lightweight MLP is optimized that is able to recover clipped wide gamut colors. This MLP model is embedded in the small gamut image. When we want to do a conversion back to the wide gamut color space, the MLP is extracted and used to restore the color values. This approach is highly effective at color loss recovery. We know that our images are encoded using RGB values. We often forget that there are many different RGB color spaces. A color space's gamut defines the range of visible colors that the space can encode. sRGB is the most common color space since most displays are capable of producing this color gamut. Note that YouTube and PowerPoint assume all images are encoded in sRGB. As a result, the larger gamut images shown in this presentation may look slightly desaturated. While color spaces are 3D in nature, it's common to visualize them projected onto a chromaticity diagram. Where are wide gamut color spaces used? Camera hardware often uses wide gamut color spaces for on-device image manipulation. A color space conversion is applied at the end of the camera pipeline based on user preference. Photo editing software, such as Photoshop, also support wide gamut color spaces. Color loss occurs during the color space conversion steps. Here we see an image encoded in ProPhoto. The sRGB and ProPhoto gamuts are shown. ProPhoto RGB values outside the sRGB color gamut are also plotted. A mask shows the location of these out-of-gamut pixels. We can also visualize this 3D plot as a chromaticity diagram. When the ProPhoto image is converted to sRGB, the out-of-gamut pixels are clipped to fit inside the smaller gamut. Now we reverse the process, mapping back from the small gamut to the wide gamut color space. Without any additional information of the original ProPhoto values, a naive conversion will not modify the clipped colors. As a result, we have lost many of the original ProPhoto colors. When we plot the original and recovered ProPhoto images side by side, it may be hard to see the difference. However, we can see the difference clearly using an error map. The goal of our work is to recover the original wide gamut color values that were lost during gamut reduction. We can visualize the quality of this recovery using an error map. Our approach is a two-stage procedure. First, during the gamut reduction stage, we apply a color space conversion to sRGB. Next, we apply the naive conversion from sRGB to ProPhoto. Here, the ProPhoto values are clipped. The key observation is that we now have access to both the original ProPhoto values and their corresponding clip values. We train an MLP that takes a 2D pixel coordinate and its clipped RGB value. The MLP predicts the original ProPhoto value at this 2D location. The MLP can be learned using a simple L2 loss against the original ProPhoto values. The trained MLP can then be embedded inside the sRGB image. During the gamut expansion stage, we apply the naive color conversion from sRGB to ProPhoto. We then extract the MLP. Clip values are processed by the MLP to recover the original ProPhoto values. We compare our work to soft clipping, an alternative to hard clipping. Soft clipping compresses out-of-gamut colors to lie within a dedicated region just inside the sRGB's gamut boundary. Soft clipping, however, distorts the sRGB colors as shown in the error map. Because of this distortion, hard clipping is preferred over soft clipping. We also compare with two prior methods targeting gamut recovery, in particular our own work called ProPhoto sampling that embeds a small amount of ProPhoto colors inside the sRGB image. These ProPhoto samples can be used for gamut recovery. We also compare against our prior deep learning method called GamutNet that trains a deep network on clipped and unclipped ProPhoto pairs. Similar to GamutNet, we test our approach against general image-to-image translation methods, namely Pix2Pix, Pix2Pix HD, and ASP.NET. Finally, our work is inspired by coordinate-based MLP methods such as siren and foray features. We are also interested in methods targeting fast MLP optimization. We compare our results against siren for gamut recovery and use the work by Mueller and others for optimization. Similar to NERF methods, we first encode our 5D input using sine and cosine functions. The MLP itself is composed of two hidden linear layers. The MLP predicts residuals that are added to the clipped values. The MLP is optimized using 20% of the out-of-gamut pixels and 2% of the in-gamut pixels. The work by Mueller and others is used for fast optimization. We also pre-train a meta-MLP on random ProPhoto images. The weights of the meta-MLP are used for initialization. We prepared a new dataset for this work. Raw camera images were selected from 4 existing datasets. The raw images were rendered using Adobe Camera Raw to ProPhoto with 4 different picture styles. From these rendered results, images were further filtered based on various criteria, the main one being the number of out-of-gamut pixels. Our final dataset consisted of 2,200 images. 2,000 images were set aside for training DNN-based methods. 200 images are used for testing. See paper for additional details. This table summarizes our results. Shown are the various methods, the amount of metadata used, where applicable, the root mean squared error and PSNR for the entire image and the out-of-gamut regions only. We also show optimization times for the MLP-based approaches. Note that the deep learning methods are all retrained on our dataset. We can see that the methods that optimize per image perform better than pre-trained deep learning models. ProPhoto sampling also works well, but requires more metadata. Siren also performs well, but is slow to optimize. Our MLP and its variants achieve the best results. The last row shows that our MLP using feature encoding, meta-MLP initialization, and fast optimization provide good results with a small 23 kilobyte model requiring less than 2 seconds to optimize. The following shows qualitative results: clipping, soft clipping, pix-to-pix, pix-to-pix HD, ASP.NET, GamutNet, ProPhoto sampling, siren, R gamut MLP. Clipping, soft clipping, pix-to-pix, pix-to-pix HD, ASP.NET, GamutNet, ProPhoto sampling, siren, R gamut MLP. We have presented a method to recover wide gamut color values lost due to gamut reduction. Our approach optimizes a lightweight MLP during the initial color space conversion. The optimization can be performed in less than 2 seconds using a GPU, and the MLP model can be embedded in the small gamut image with minimal overhead. Experiments show this approach performs well compared to competing methods. As part of this effort, we have prepared a high-quality dataset comprised of over 2,000 images to support research in this area. Please visit our webpage found at this link.